Now let us talk about Riemann-Roch spaces. So say you're given a divisor like this, np times p. Np is an integer, p is the point on the curve. So this curve lies in some projective space. So to this divisor D, we can associate a vector space L of t. So what does this consist of? This consists of all the functions which lie in this field of fractions of the curve, such that divisor of f plus t is greater or equal to 0. So when you take divisor of f and then add d to it, you do the coordinate wise addition, you get a new divisor. So that new divisor is, say, e. Now we are saying this new divisor is effective. So this new divisor will also be of the form np times p. So we are saying that all these integers after addition should be positive. And then we make a union with 0 just in case 0 is missing here. You add 0 because essentially we want this L of t to be a vector space. So what does this mean in words? So you're given this divisor D. So at some places this np would be less than 0, and at some places this np would be greater than 0. So if np is less than 0, then the function which you add to it should have zeros with multiplicities at least np, because when you add to this it should become positive. So if this is negative 3, you should have your function with zeros at point p which are more than 3, because then you can have some positive number. Similarly for poles, so wherever this np is positive in D, then corresponding to it this f will have poles with multiplicity at most np. So the best part is if the f does not have poles at all, then obviously this divisor at that point would be effective, because this np is anyway positive to start with. So the problem arises that if f has poles, how many poles should it have? It should have at most np poles, obviously all of these at point p. So basically this space tries to put some kind of condition on poles as well as zeros of this function. So there's some condition on poles and zeros of the functions which lie in this space. So this is more clear with example. So let us see an example. So say we are working in space, say p1. The curve is p1, say. Now you're given a divisor like this, minus 0, 1, 2, 1, 0. So these are two different points. So say this is point p2, this is point p1, and this minus means minus 1 times point p1. So this divisor is essentially of this form, minus 1 times p1 plus 2 times p2, where p1 and p2 are just precisely this. So now say you are given a function like this, x plus y over y square. So again we are working in space p1. Notice that degree of numerator is equal to degree of denominator. So what is the divisor of f? So first you consider 0. So 0 is where x is 0. So x is 0 right here, x is 2y. And then where this is 0. So this is 0 when x is equal to negative y. So this is when the numerator is 0, and denominator is 0 precisely when y is 0. So x is 2y, y is 0, and then you put minus 2 because of the 2 right here. So 2 poles. So now divisor of f plus d, you just add coordinate wise. So now we have this will cancel with this. Then you have minus 0, 1 plus 0, 1. This will cancel with this. So you just have this. So 1 is to minus 1, and this is effective. So notice this is greater or equal to 0 because you have 1 times the point. So f lies in L of t. So now we consider a new function g. So g is nothing but 1 by f. So now y squared becomes numerator, x times x plus y becomes denominator. So what is divisor of g? So everything here but with the opposite sign. So 2 minus 1 times 1 this, and then minus 1. We're copying exactly this. Signs are reversed. Now you add d to it. So now this 2 plus 2 will give you 4. This minus 0 is to 1 minus this minus 1 will give you minus 2, and this comes as such. So notice that this divisor is no longer effective because you have minus 1 times a point here and minus 2 times a point here. So this is some other point. This is positive. So this is effective here, not effective here, not effective here. So G does not lie in your vector space here. So notice that F lies in here, but this 1 over f does not lie in this for our given divisor d, which is minus 1 times a point and then plus 2 times a point. So let us see some more properties. So let us see some properties of the space LD. So the first property is L of 0 is 1. So say your degree is given to you as 0. Now if the degree is 0, then the function cannot have any poles. So the function cannot have any poles. So the function which lies in your space L of t, it has no poles. But we are working in projective space. Our curves lie in projective space. So this function is of the form something like g by h, where degree of g is equal to degree of h. So number of zeros has to be equal to number of poles. But since this function has no poles, it will also have no zeros, because you need the degree of numerator equal to denominator. That is, number of zeros has to equal to number of poles. If number of poles is 0, the number of zeros will also be 0. So the only thing this function can have is constants. So the constants have neither poles nor zeros. So this is the first part. So the constants lie in the space L of 0. Number 2, your degree is given less than 0. So obviously constants don't lie in this space. So 1 is not in this space precisely because these constants have degree 0 and this is less than 0. So again, if this is less than 0, what we are saying is that the function can only have zeros. Your function can only have zeros, because after all you could have to add positive number to these negative numbers to make your divisor effective. So notice this sign. So the function can have only zeros. So if function has only zeros, this is not possible in the projective space, because again, if it has zeros, then it has to have poles. These always come together in projective space. So if it has no zeros, no poles, and no constants, so only element left is now this 0. And that is this. So number 3 is this. So number 3, degree is 1 times certain point, and that point is 1, 0. So 1 times 1 of 0. So now you can have poles on functions, but these poles with a multiplicity at most. So at most n of p. So the poles with multiplicity at most 1. Again, we are working in projective space, so you have to have zeros and poles. So the only function you can have is x by y. So this will vanish here. So this lies in the space, and obviously constants lie in the space, because constants are just 0, and then 0 plus 1 of 0 is still effective, which is 1 times 1 of 0. This is greater or equal to 0. So again, effective divisor, just by definition. So this is done. Number 4, if you add a point, you increase the space. So obviously when you add a point to the divisor, you are basically saying that you can increase number of poles. So you can increase number of poles. So you're increasing the bound on the poles. But L of d already has functions with poles which are obviously less than this. So adding some point p to your divisor is not going to break anything. All the functions will already be included in here. Now this you can generalize. If d1 is less than or equal to d2, then ld1 lies in ld2. So this obviously you can see this way is that this thing you can write it as an effective divisor is d2 minus d1. And this effective divisor just consists of adding points, say p1 plus 3q and so on. So these p and q are points. So you're adding just points to it, and you keep adding points, you're just increasing the number of poles. So you're not making any impact on the initial vector space. You're not violating the bounds of this vector space. So you're not violating any bounds here. So this makes sense. Now, as I said before, you can check the vector space axioms. L of d is a vector space, and this small l of d is how you write dimension of L of d. Now this thing right here, this translates like this: L of d is less than or equal to L of d plus p. But this again is an important inequality which we will probably show later, that L of D plus P is less than equal to L of D plus 1. That is, if you add a point, you can at most increase the dimension by 1. So this to be shown later, and this we have just shown.